Right, this is part 3 of the Mantissa exponent saga, and it's all about getting the technique right. So I've given you this binary number. The question in the exam could be: a floating point number system uses 16-bit numbers 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 8 bits for the signed Mantissa, and 8 bits for the signed exponent. Notice in the exam they will tell you which is which. Convert the following binary number to denary. Denary, I beg your pardon. Step 1, ID, the exponent. Okay? In other words, identify the exponent. There it is. We always identify the exponent first. Why? Because we want to know how many positions to move the binary point, the decimal point if you like, but in this case, because it's binary, we call it the binary point, how many to move it, and to move it either right or left. Then identify, is the exponent positive? Yes. The exponent value is 4 plus 1, which is 5. What's 4 plus 1? Well, that's 1, that's nothing, and that's 4. So that's 5. Our exponent is 5. We don't worry about the leading zeros. So, here we go. The sign, yeah, the 0. We've got that, we've got that, we've got that. Sorry, just breaking it down. We need to move on. Step 2, identify the Mantissa. Alright, the Mantissa is basically that. We've done that. Why? Because in the first part of the Mantissa, it is always, okay, the indicator of whether the Mantissa is positive or negative. Okay, so we can safely say 0 point, because the first bit, most significant bit, MSB, is going to tell us positive or negative. Remember, 0 is negative. Positive. So, is it positive? Yes. Now, step 3, the exponent is 5, so move the binary point 5 times to the right. Remember our exponent, there it is, was 5. So we're going to move the point 1, 2, 3, 4, 5 to the right. And I've animated that for you. There we go. And the animation didn't work quite right. The point should be there. Drats. Anyway, yeah, that's better. Although it's dropped out of there. Anyway, so this is our conversion steps. We're up to step 3. Now what? Well, our aim is to end up with a decimal number. So let's have a look. That's our original number. Step 4, we've got that number now. It's positive. And we've got 101001, which in binary is converted to decimal 19. Okay. The 0.1 is our fractional component. The 0.1. So the exponent only told us how many places to move the binary point. We now are referring to decimals, so we're referring to a decimal point. The binary point is 0.01, which converts to 0.25. Okay, so I hope you can put this number together now. And yes, I'm sure you got that one right, 19.25. That's a bit of helpful sheets I always have to hand. I've noticed in the exam they like to push it to here sometimes. Okay, so fractional component in that example is 0.25, but in the exam, be aware, they might throw that at you, 0.0625. So this is the question from that exam. This is a floating point representation of a number. Okay, straight away, what are you going to do? What is the first step? What comes to mind? I'm not going to go back in the slides. You must now have step 1, ID the different parts. They've actually made it easier for you by putting the decimal in. Alright, in the previous example you had to put the decimal in, but the decimal has been put in, and the first part is our most significant bit that tells us, is this a positive or negative number? What number is this? It's positive. This is our Mantissa, this is our exponent, and in the exam they actually tell you this. The exam question was, calculate the denary equivalent of the floating point binary number. ID the exponent. Is it positive? ID the Mantissa. Is it positive? This is both positive. Convert the exponent. 6. What does the 6 mean? So step 4 is now all about moving the decimal 6 places. Well, it's positive, so the exponent is positive, so we move the decimal 6 to the right. There we go. 1, 2, 3, 4, 5, 6. Okay? There it is there. We've got the answer. So what is the denary of that? What is the decimal number there? Take a moment to try and work it out yourself. It's 40. Great. Couple of marks in the exam. They like you to show the working out. Any conversion that you show is good, gets you the marks. Any conversion. Or writing down, move binary 0.6 times. Okay? Now, write the normalized floating point representation of the negative denary value minus 7.75 in the boxes below. Show how you have arrived at your answer. So, whoops, shoved ahead there, hold on, let's get back, yep. So what do they want you to see? At least this. What is this? This is the 2's complement, if you like. This is the flipping, where we have to go through the process of understanding a negative binary number by flipping each of the binary digits. So 7 in binary is 111, 0.75 in binary is 0.11. So all of that flipped is 0.00. Or we could also in our workings explain that it's fixed points 2's complement and so on and so forth. How we add the 1, alright, for 2's complement, so it becomes 0.01. But we show the fact that it's a negative number with the 1 in front. That's important. Okay, so any of these will get you the 2 marks, but especially they'll give you an award. Have I got a note from the examiner on that one? Let me just have a look. Yeah, examiner's note. Both working marks awarded if the bit pattern 1.00001 is shown anywhere. You show the that basically you show that how you got to that answer. Don't worry about these trailing zeros, and they'll be happy as well. So the answer is 1.0000100, and the exponent is 0011. Okay, 0011, and that's your other mark. Right, last but not least, there can be a loss of precision when a denary number, a decimal, is stored using the floating point system. The closest possible representation of denary number 6.9 is shown below. I will make this into another part because this is a slightly different way of interpreting and understanding the fact of efficiency or accuracy, precision and range. So accuracy and range that you get within an integer. And we need to talk a bit about unsigned integers as well. So we'll stop it there and just remember that it ended with 2C from the exam.